There are these invisible engines that power pretty much everything in our modern world. They're in our cars, our power plants, even our kitchens. And they all run on just a few simple, repeating recipes for turning heat into, well, action. So how on earth do they actually work?
I mean, it really does seem like magic, doesn't it? But it's not. The answer to both of those questions lies in the exact same fundamental principle of physics, just kind of flipped upside down. We're about to dive into the elegant, powerful world of thermodynamic cycles.
At its absolute heart, the whole concept is beautifully simple. You take a substance, think air or water, and you put it through a series of changes. You heat it, you cool it, you squeeze it, you let it expand, and by doing that, you get it to do something useful for us, like push a piston or spin a giant turbine.
Okay, so here's the textbook definition. A thermodynamic cycle is basically a closed loop of processes. A substance, like air or steam, goes on a journey and ends up exactly where it started, ready to do it all over again. But in that one loop, it's managed to transform heat into useful work. And that, right there, is the blueprint for almost every engine you can think of.
So, let's start with the one we all know best, the engine humming away under the hood of your car. Most gasoline cars run on this really elegant four-step process called the Otto cycle.
Now, those terms sound pretty technical, but we can make it way simpler. You might have heard this called the suck, squeeze, bang, blow cycle. The engine sucks in a mix of fuel and air, it squeezes it tight, a spark plug ignites it for the bang, that's the power stroke, and finally, it blows out the exhaust. This little four-step dance happens thousands of times every single minute.
Now, diesel engines, they use a slightly different cycle. The really crucial difference is how they get that bang. Instead of a spark plug, the diesel cycle just compresses the air so much that it gets incredibly hot enough to ignite the fuel all by itself. This means the fuel gets injected and burns while the piston is already moving down, which completely changes how the power gets delivered.
And this difference leads to a really fascinating trade-off. See, if you could build two engines with the exact same compression ratio, the gasoline-powered Otto cycle would actually be more efficient. But here's the thing. In the real world, diesel engines are built to handle way higher pressures. So if you compare them based on the maximum pressure they can take, the diesel cycle pulls ahead in efficiency. It's all about those real-world engineering constraints.
Okay, let's zoom out from our cars for a second and look at the massive cycles that power our entire civilization. Now we're talking about the real giants of the industry, the cycles that give us electricity and let us fly across oceans.
First up, we've got the Brayton cycle. This is the absolute workhorse behind every jet engine. It's a continuous flow. Air gets sucked in, it's compressed, fuel is added and ignited, and then that super hot expanding gas spins a turbine. In a jet engine, that turbine's main job is to keep the compressor going, while all the rest of that hot gas blasts out the back, and that's your thrust.
Now, what if instead of using air, you use water? Well, that's the whole idea behind the Rankine cycle. And this isn't just another engine. This is the cycle that generates most of the electricity on the planet. It's the reason our lights turn on. It's the heart of coal, nuclear, and natural gas power plants, a true titan of the modern world. The whole process is this big, powerful loop. Water gets pressurized, then it's boiled into high-pressure steam. This steam blasts through a turbine, spinning it like crazy to generate electricity. Then it's cooled back down into water to start all over again. But the real magic, the incredible power, comes from that phase change. When water turns to steam, it expands to over 1,000 times its original volume. That unbelievable force is literally what drives our world.
So far, we've only talked about using heat to create motion. But what if we wanted to do the exact opposite? What if we wanted to use motion, or work, to move heat from one place to another? Well, that's the secret behind every refrigerator and air conditioner.
That's really the core idea right there. Instead of letting heat naturally flow from hot to cold to create work, we're going to put work in to force heat to move from a cold place to a warm one, the exact opposite of what it wants to do on its own. And this is the cycle that makes it happen, the vapor compression refrigeration system. Now, I know this diagram looks a little complicated, but it's really just a map of the process. It shows how a special fluid, a refrigerant, keeps changing its state to achieve one simple goal: pump the heat out of a cold box and dump it somewhere warmer.
Okay, so here's how it works. Inside your fridge, a very cold liquid refrigerant boils and turns into a gas. In doing that, it absorbs heat, which is what makes the inside of your fridge cold. That gas then goes to a compressor. That's the humming sound you hear, which squeezes it and makes it really hot. This hot gas flows through the coils on the back of your fridge, releasing its heat into your kitchen.
Finally, it goes through a tiny expansion valve, which makes it an intensely cold liquid again, ready to go back inside and repeat the whole cycle. But you see, for engineers, just making a cycle work is never enough. The real challenge, the constant obsession, is making them more efficient, squeezing more useful work out of every last drop of fuel.
And they have some seriously clever tricks to do it. There's reheating, where you give the steam a second blast of heat partway through the turbine to give it an extra kick. There's regeneration, which is a brilliant way of using the hot exhaust to pre-warm the fluid going back in, which saves a ton of fuel. And intercooling, where you cool the air as it's being compressed, which actually makes the compressor's job easier and the whole cycle more efficient.
So in the end, whether you're talking about the deafening roar of a jet engine or the quiet chill of a refrigerator, it all comes down to these repeating cycles. They are the fundamental rulebooks for manipulating heat and pressure to do whatever we want. It's all about mastering the directed flow of energy.
And that kind of leaves us with a fascinating question, right? The Otto, the Rankine, the Brayton cycles, they were born from steam and steel, the absolute cornerstones of the Industrial Revolution. But as we look towards solar and hydrogen, or even fusion power, what new, brilliant cycles are we going to invent to harness the energy of the future?